All right, so we concluded the last PowerPoint with kind of tempering our excitement about graphical summaries and data visualization. We said, man, there's always kind of cool plots that we can make. We focus primarily on histograms, but right, there's no shortage of endless plots, and it's very exciting. It's very cool. It's actually, no kidding aside, we're in a little bit of a data visualization renaissance. But that said, we tempered that excitement by acknowledging that there are some shortcomings for these visual summaries. Part of the shortcomings is that they only give rough subjective feels, particularly with respect to notions of average and notions of variability. And there also could be arbitrary. When we're talking about histograms, the number of categories is sometimes a little bit arbitrary. When we're making things like scatter plots, sometimes the scale that's picked to actually graph the scatter plot, right, can have a certain bit of arbitrariness to it. And so particularly when we want to describe or measure things like average and variability, it's nice to have something more black and white, something more concrete, something that if you were to do it and I were to do it, we would actually always come up with sort of the same answer or the same measurement. And so that's what we're going to talk about in this PowerPoint. That is numerical measurements of average and variability. So numerical ways of measuring the average, there's sort of three main ones. I imagine you're familiar with all three. There's the mode, it's the value that occurs more than any other. There's the median, that's the 50th percentile. And there's the mean, that's add them all up, add up all observations, and divide by the total number of observations. So what are like the pros and cons? Well, the sort of the pro for the mode, the kind of the feather in its cap, and really like the only feather in its cap, is that the mode works for categorical data, whereas the mean and median typically do not, right? So if you're looking at a bag full of M&Ms, you pull out an M&M and you record its color. And you do that over and over and over and over, right? You can compute the mode color. The mode color is just the color that occurs more than any other, right? However, you can't really do a mean color. You can't add all the colors up and divide by the size of the sample. And you can't really do the median, right? Median is you numerically rank your observations and take the middlemost one. You can't really numerically rank the colors. So mode is nice in the sense that you can use it for categorical data, but beyond that, we tend to avoid using it. In fact, nowadays a lot of textbooks don't even teach the mode, because the mode can be deceptive for numerical data and or non-informative, right? So I mean, imagine like a test score where everyone did really poorly. One student got a 30%, one got a 31, another got a 32, another got a 33, a 34, a 35, 36, 37, 38. Everyone's in the 30s. One student though did really, really well, although just between you and me, right, they're kind of like these geniuses and they've already kind of taken this class, but they're being forced to take it again. They get 100%. And then someone copied off them and they got 100% too. So there's two 100s and a bunch of right values in the 30s, but none of them are replicated, 31, 32, 33. So in that case, the mode's what? The mode's 100? But we'd probably be pissed if the teacher came in and said, oh, great news, the average was 100. So there's obviously no need to curve this test. Well, that's silly, isn't it? And the mode often could lead us to sort of silly ways of describing or measuring average. So we tend to avoid using it. And so we typically pick between the median and the mean. Now when picking between the median and the mean, one thing we want to keep in mind is the median is what we call a resistant measurement. A resistant measurement is a measurement that is not extremely influenced, that's not unduly influenced by just a small amount, by just a handful of really big or really small numbers. So that's a feather in its cap. The mean, however, is not resistant. So it's a little bit of a black mark, whatever the opposite of a feather in the cap is for the mean. Let's look at this idea of resistance a little bit more closely. So here's an example. Imagine we're hired by the University of North Carolina, it's the great Professor Rieger's alma mater, to write a pamphlet advertising their cultural geography program. That sounds kind of cool. So they want to advertise their cultural geography program. And of course, part of what they're going to advertise in their colorful pamphlet is right, how exciting it is and all the cool things you can do. But part of it, they want to say, right, how much you can expect to make on average after graduating with this degree, particularly a degree from, right, the prestigious UNC. And so if they want to find out how much their alumni are making, they're going to have to make a phone call to, right, students that have graduated with this degree, do a survey, and ask their alumni, like, hey, how much are you making? So they call 5 alumni, they say, how much are you making? And the results of their little 5-person survey are going to be on the next slide. So first student, $40,000, not too shabby. Next student, $50,000. Wow, you're doing well for yourself. Congratulations. Next student, $30,000. All right, not as high as the other two, but don't give up hope. Maybe you're just getting started. Kind of stick at it. Persevere. Whoa, $20 million? $20 million? Is that a typo? Let me go back to the records. No, it's $20 million. I kind of feel bad for that 5th person, don't you? Because I feel like under normal circumstances we would have been impressed by that 60,000, but right after that 20 million, it kind of feels like a little bit ho-hum. Now I leave it to you to verify the median is 50,000, right? Because you gotta order those numbers, and then after you order them, you pick the middle one. The middle one should be 50,000, after they're ordered. To do the mean, we add them all up. And we divide by 5 in this case. So the median salary is 50,000. The mean salary is 4 million. Big difference between the two, right? With just one number that's outside of the pattern, admittedly well outside the pattern. Probably between these two numbers, most of us would probably think is the median as more accurately portraying what we would consider kind of this notion of average salary. The mean is pulled towards that one large number. The mean is pulled towards that 20 million, and so it's distorted. It's kind of unrealistically deceptively high. Does that make sense? In fact, we could change that 20 million to 200 million, couldn't we? And the median is not going to budge. It's resistant. The mean, however, would change quite a bit and will be pulled again well towards that 200,000. Now, in this example, what happened? Well, it turns out, of course, the great Michael Jordan, basketball legend, UNC graduate, degree in cultural geography. I guess we kind of hit the jackpot, and we accidentally sampled him as one of our 5. And if we were computing means, that would have thrown things off. But if we were smartly using the median, well, everything would be fine. So in summary, the mean is inappropriate to use for samples that have a handful of extremely large or extremely small values. This is the same as saying that the mean is inappropriate for skewed distribution. So this goes back to our last PowerPoints. Our last PowerPoints, we said one of the first things we do is we make a histogram. In the histogram, we ask ourselves, is it skewed or symmetric? Why? Because whether it's skewed or symmetric is going to guide our decision as to what the appropriate measurement of average is. Right? A skewed distribution has these tapering tails. These tapering tails are representing just a handful of really big or really small numbers, depending on which way that tail is tapering. For a right-skewed distribution, where the tail tapers off to the right, our mean is going to be pulled towards those handful of large values. Our mean is going to be larger than it should be. The mean will be larger than the median. For a left-skewed distribution, where the tail tapers to the left, we have a handful of really small values. They pull the mean towards that left to the left, and so the mean is going to be sort of smaller than it should be. It'll be smaller than the median. So, I mean, this is reflected in real life. That is, right? If you go to the Bureau of Labor Statistics and you look up average salary for statisticians or any other profession, the average salary that the Bureau of Labor Statistics is going to report is a median salary. Why? Why is the Bureau of Labor Statistics reporting a median salary? Because it is a well-accepted fact that salary follows a right-skewed distribution. And it's a statistical fact that it is inappropriate to use the mean for skewed distributions. So instead, the Bureau of Labor Statistics reports the median. Same when you're getting ready to buy a house, right? So if you've bought one or you're getting ready to buy one, you start looking at certain neighborhoods. Hey, I want to move here. Hey, I want to move there. I want to see if I can afford it. So I'm going to look up the average housing price in that neighborhood. They're going to report a median house value or median home value. Again, why? Home value tends to follow right-skewed distributions. Pretty cool, right? Well, what about measurements of variation? So center is just one part of the picture. Another important piece is trying to, for any particular variable or any particular distribution, we will also want to have ways of measuring its variability, its dispersion. Are all the values very, very close to one another, or are they diffuse and spread out from one another? There's three common ways of measuring variability. The first is the range. We'll talk about what that is in a second. The second is variance / standard deviation. We'll see that they're sort of related to one another, which is why I put them on the same bullet point. And the third one is the interquartile range. So the range is just the largest value of the variable minus the smallest value. So, right, remember subtraction's a distance operator. So we're just looking at, right, how far is the spread between the largest and smallest. All our observations are contained within that range of values. Pretty straightforward, pretty intuitive, pretty easy to calculate. Variance a little bit more complicated. So the variance could be thought of as the average squared distance that all observations are from the mean. It can be computed with the following formula. So we abbreviate the sample variance. We abbreviate it with s squared. We compute it with that following formula. So that's the capital Greek letter sigma, capital sigma. In math, that's the add 'em all up symbol. I got lazy with my subscript, but the x's should sort of be x sub I. So the x's are the observations. So what we're basically doing, for every observation, we're doing the observation minus x bar, which is saying what's the difference, what's the distance between our observation and the sample mean. And then we square that distance. So we have a bunch of squared distances. We average the squared distances. We add them all up. We divide by n minus 1 instead of n, right? If we were computing an average, n is what we would expect. N minus 1 is very, very close to n. It turns out we could prove this. In fact, you might prove it in 506, that we want the sample variance to be a good guess, actually to be a best guess, for a population variance. That is, we want to compute the variability in our sample in a way that it's a good guess for the variability in our population. And it turns out you can sort of prove mathematically, maybe a little unexpectedly, that to make it the best possible guess, we have to divide by n minus 1 rather than n. It turns out if you divide by n instead of n minus 1, that it ends up being what we call bias. It ends up being just a little bit smaller than it should be. And so it's not a unbiased estimator, which is what we want it to be. But again, kind of quibbling, n minus 1 is awfully close to n. So I mean, it's kind of looking at the average of these squared distances. Now the variance is in these weird squared units, which is often kind of hard for us to interpret. So like the variance of salary is in like units of square dollars, whatever a square dollar is. Right? The variance of weight would be in square pounds, whatever a square pound is. And so because of these kind of weird kind of nonsense units, that sort of motivates us taking an extra step. We take the extra step and we turn that variance into something called a standard deviation. The standard deviation we can think of as not the average squared distance, but the average actual distance that all observations are from the mean. And we sort of move from the squared distance to the actual distance by just taking that variance and square rooting it, right? Pretty straightforward. So the sample standard deviation, denoted S for standard deviation, that makes sense, is just the square root of the variance, right? We look at that square root, and what's underneath that square root is the variance formula from the previous slide. Now, before I move forward, let me ask you this. Do you think that either of these measurements of variation are resistant? Do you think the range is a resistant measurement of variation? You're right, it's not, right? I mean, the range is calculated using nothing but the largest and smallest value. So of course it's going to be unduly influenced by the largest or smallest values, right? I mean, it only uses the extreme values, so these extreme values are sort of all that impacts the range. And so the range is very, very, very not resistant. Now, maybe a little bit more subtly, we think of the standard deviation. We think of the standard deviation, right? The standard deviation, its whole formula, its whole interpretation is based upon the sample mean. And remember, the sample mean is not resistant. The sample mean is inappropriate for skewed distributions. So it makes a little bit of sense that anything based off of it, anything in which the mean is its foundation, is probably also not going to be a good fit for, skewed distributions, and also not be resistant. So we're left at this point with what? We're left at this point wanting some resistant measurement of variation. And here it is. Lo behold, the interquartile range. The interquartile range is the third quartile minus the first quartile. Sometimes the third quartile is called the upper quartile. Sometimes the first quartile is called the lower quartile. The first quartile is defined as the 25th percentile of the variable. So it's the value such that 25% of the observations are below it. Flip side, 75% or more than it. The third quartile is the 75th percentile. And so the interquartile range is the spread between these two numbers. Now, does it make sense that this is resistant? Because what are we doing? We're really sort of trimming away that upper 25%, the extremely large values. And we're trimming away that lower 25%, the kind of extremely small values. And we're looking at the range then of these sort of middle-ish numbers. And that gives us the interquartile range, which becomes a resistant way of measuring variation. So, to bring it all together, to summarize, to adequately describe a particular data set numerically, we need at least measurements of average and measurements of dispersion, measurements of center and spread. Now, for reasons that are maybe not obvious to us now, our goal as researchers is to always use the sample mean whenever possible. Based on what we've talked about right now, that maybe seems a little bit strange, right? Because the median feels like a little bit more intuitive, it's resistant. We would think maybe we should be using the median as much as possible. But there's a very special reason that we'll talk about, like maybe PowerPoint 5-ish. A pretty profound reason that we try to use the mean whenever we can. So symmetric data sets it's no problem. For symmetric data sets, the mean is a very reasonable way of describing average. So for symmetric data sets, we use the mean and we pair it with the standard deviation. Now, if we have a skewed data set, well, we saw an example, right? The Michael Jordan example, where the mean is inappropriate. it gets distorted, it gets screwed up, it gets messed up by the handful of big or small numbers. So instead we use the median and we pair that median with the interquartile range, or alternatively we sometimes use something referred to as the 5-number summary. 5-number summary is just the minimum, the maximum, the first quartile, the third quartile, and the median. So 5 numbers that summarize typically a skewed distribution. And that's I think that's it for descriptive statistics. Time to move on to the exciting world of inferential statistics.